So welcome to my talk on the hidden art. No start? Whoa. I thought you want me to start. No start? Oh, the music. Come on, that's even better. Have some music. I thought there was supposed to be the music. Oh, this is boring now. Just my voice. So people ask me, is it my first time in Luxembourg? And no, it's not my first time in Luxembourg. I was in Luxembourg in 1982. It's a long, but I wasn't here for long. Back in the day, I used to fly, I flew from South Africa as a child to Germany, and the cheapest flight was via Luxembourg. In those days, Luxembourg was the cheap airline. Things have changed a bit. And you would get the Benelux visa in those days. So yeah, it's not my first time, but it's for practical purposes my first time in Luxembourg, and I've enjoyed it so much so far. A friend of mine told me Luxembourg is like Germany where they speak French. So I'm not sure if that's an insult or a compliment. I don't know. But it's been fun so far. So thanks for inviting me, and thanks for having me. So we're going to look at java.util.concurrent in great detail today, a very deep dive, so it's a very specialized topic. And I'm going to start with a class we all know, java.util.vector. It's been with us since Java 1.0. And java.util.vector was supposed to be thread safe from the beginning. So for example, most of the methods are synchronized, not all, but most. And they were all locking on the object itself. But they missed some important synchronization. For example, on the size method. The size was not synchronized. They said, well, it's read-only, what do we care? And then they also didn't mark the element count as volatile, which meant when you read the size, you could get stale values back. So another thread might change the size, but you wouldn't see the element count. So this is a little bug in Java 1.0. And then Java 1.1, they changed vector a little bit, not too much, but they made vector to also be serializable. And by making it serializable, they introduced a potential race condition. Because what could happen is that you could write vector into a file or over the network, and at the same time, another thread could change it. There was no synchronization at all between writing it on an output stream and changing it. So there was no change like that. And this stayed like that for a number of years. In Java 1.4, they changed that, and they actually fixed both bugs. So they fixed the one bug, the race condition. They changed that by adding a write element, a write object method, which was synchronized. And they also made the size method synchronized so that both methods are synchronized, and you always see you don't see stale values anymore, and you also don't have this race condition on the writing of the object into the stream. However, by fixing the one problem, they added another problem. So what could happen now, if you had a very strange, really, really weird data structure, you had a vector 1 which contained vector 2, and vector 2 which contained vector 1, and you wrote vector 1 and vector 2 from two different threads at the same time, you could cause a deadlock. And I noticed this a long time ago, my news at 184, and I wrote about it, and I made a comment saying, this would obviously never happen. There's no ways somebody would write such a crazy data structure. However, there was the IBM code actually was implemented slightly differently because somebody had reported a bug on the IBM virtual machine for this exact problem. So some of the IBM customers decided to do something like that. I don't know if it was real code or play code. Java 1.7 they change this a bit, and they basically, what they do is they make a clone of the underlying array inside the synchronized block, but then they do the writing of the fields outside of the synchronized block. And this gets rid of that deadlock, potential deadlock. And so now vector works again. So it's like the first version of vector that was, should we say, correct. But they didn't keep it correct for very long, because Java 1.8, they added for each synchronized. And so if you have two vectors, and the one calls for each, or you call for each on both vectors and they refer to each other, they don't have to contain each other, they just have to do something, like call size on the other vector. Again, you can get a deadlock. So there are lots of possibilities how you can get yourself into trouble with any class within the JDK. So there's some takeaways from this. First of all, the whole thing with thread safety is a little bit subtle. You don't, and you might have a test, and the test might sometimes fail. And if a test fails 1 out of 1,000 tests, you're probably going to simply ignore it and try it once more. And then it'll work, and you go, oh, I don't know why it didn't work, and now it's working, so all's good. And so when we are testing for concurrency bugs, most of the time we need to know exactly what to look for. And if we know exactly what to look for, then we might be lucky in finding the problem. Oh, I just have to say who I am. So I'm Heinz. I'm the guy that makes the ketchup. No, not really. I write the Java Specialist newsletter. I've been doing it for about 25 years. If you want to have a look at that, pop over to javaspecialists.eu. I speak at conferences. I teach Java. I'm also a Java champion. Not the only one here. Saw 2 others too. All right. So let's continue and look at this java.util concurrent. So java.util concurrent, writing thread-safe code is challenging. And the reason it's challenging is we've got a rule book. We've got these laws. And the laws are described inside the Java memory model. And the Java memory model says information about what happens before what, ordering, access, safety, and so on. And the memory model is basically the rule book for how threads would interact with each other. How does memory get managed between threads? If threads never shared memory, we wouldn't need this rule book. But we've got this rule book. The problem is that there's no way of testing whether our classes adhere to the Java memory model 100%. And we can run our code, and it might work perfectly well on Intel, and then we go to ARM64, and our code might fail because it broke one of the rules of the Java memory model, but we didn't realize that. And so sometimes it's really hard to detect the bugs. We run the code, we hope it works correctly, and really one of the best ways to find the bugs is to have lots of people use that particular code. Now, I'm busy recording a very detailed walkthrough teardown of the Java.util concurrent classes, and what I've started looking at is a class called lock support. And there's an example inside lock support where they've got some very strange code where they have a static block and they say, and they load the lock support.class class. And I couldn't figure out why they would need this. And I started digging around, and I found this code all over the JDK. Basically, wherever lock support was used, they would have at the bottom a static block that would load the class. Not initialize it, but just load it. And what happened was there was a bug that Martin Buchholz discovered working at Google, where sometimes a thread would not get unparked. It would get parked, but not unparked. And he had to run the code, his test, for a whole week in order to get one example where this happened. This was Java 7, right? And so the workaround was you put a static block only for classes where you use lock support. If you don't use lock support, you don't need this. And the problem sort of seemed to go away in Java 8, but nobody really knows whether or not. And I noticed when I looked at the code that the only places where they don't have this is with the new Project Loom classes that use lock support. So I logged a bug, but I said, I don't know whether this is a problem or not. And no one could tell me either. So there's no definite yes or no. The bug is just going to be like, go stale eventually. And it's sometimes these bugs are really, really hard to reproduce. And really hard to prove that you don't need, that it's working correctly. All right. So why should you study these Java concurrent classes? First of all, Brian Gertz in his famous book, Java Concurrency in Practice, says basically that don't write your own synchronizers, use what's there. Don't write your own. If you find something which fits, use that, don't write your own. And by studying the Java concurrent packages, we can find out, first of all, what is available that we can use to solve our problems. And then also, we can learn the techniques that are used to write robust thread-safe classes. So we learn both at the same time. And we all make mistakes, of course, and even the best coders make mistakes. In German, we say, Vertrauen ist gut, Kontrolle ist besser, right? We can trust, but it's better to check up on that trust. And so we do that with test-driven development, but as I said before, it's really hard to do that with multi-threaded code because you need to know what you're looking for, and then sometimes you need to run your code millions of times, maybe for a whole week, to find the problem. And if you don't find the problem, it doesn't mean it's not there, it just means you haven't found it yet, right? So because of that, I recommend that you use well-known synchronizers that others have used as well, that are in wide use. For example, if I need a concurrent map, I would prefer to use concurrent hash map rather than concurrent skip list map, because concurrent hash map is used more. And I would prefer linked blocking queue over linked blocking deck, again, because linked blocking queue is far more used than linked blocking deck. And I've been contributing bugs to the JDK. No, I've been contributing bug fixes, not bugs. I'm trying not to contribute bugs to the JDK. And I've referred to quite a few. And most of these bugs, in fact, probably all of these, are in little used classes. So for example, I found a bug in link transfer queue, one in concurrent skip list map, which by inference also has concurrent skip list set, one in array blocking queue, and 5 in link blocking deck. And they're all fixed for Java 26. So once you update the next version, you'll get all those fixes as well. And this sort of shows us, again, that the less used the class is, the higher the chance of bugs, obviously. And so, eat your own dog food. How many instances are there in the JDK? Well, concurrent hash map I found hundreds of times. And then these other ones, copy and write array lists, concurrent link queue, concurrent link deck, future task link blocking queue, also quite a few times, dozens of times, and the rest very rarely. So be careful of the one below, because you've got a higher probability of finding bugs or discovering bugs there. So use extremely common thread-safe classes. As I said, I only found bugs in the rarely used classes. Oh, now this is something else. I've got a little gift for those who are here. This is a coupon which expires at 5:30, so once my talk is done. But obviously you don't have to finish the course by 5:30. It'll take a while to finish that. Once you've got the course, you keep that forever. So that's a little gift. And if you want to sign up to my newsletter as well, pop over to javaspecialist.eu and you'll get that there as well. Also, tinyurl.com/voxxed-lux-25 will get that to you as well. All right, that's the data structures course. So I want to look at the striped 64. This is a really interesting class. And let's have a look at a comparison between adding up 100 million times with an atomic long versus a long adder. So this is the time where we go over to demo over here, and we're going to do this. Say int stream.range 0 to 100 million, not a billion, dot parallel dot for each. I'm going to over here make a var. Let's start with the atomic equals new atomic integer, and we're going to just say atomic dot increment and get. And we're going to measure how long that takes. That's the atomic time. And then we're going to try with a long adder. So we do exactly the same thing again. I'll just copy and paste that down here. But it'll be now an adder. It'll be an adder over here. It'll be a long adder. And long adder is a subclass of striped 64. And again, we'll put a time around that. That's the adder time to see how long that takes. So we'll run that code, and we'll see how the two compare. So the atomic integer, oh, that's quite a big difference, took 5 seconds to increment, and the adder time took 100 milliseconds to increment. All right? So that's obviously a massive difference. You know, it's like 50 times faster to do it with a long adder versus the atomic integer. So is it magic? Well, of course it's not magic. And let's have a look at how the striped 64 actually works. So the way that striped 64 works is that internally, so this long adder is a striped 64, it contains the value as a long. So the actual value, the shared value, is a long. And then what they do is they try and update that value from just with a normal compare and swap, or compare and set. They try and update it. If they manage to update it without losing the race for the compare and set, then everything is fine. In other words, if you have one thread doing an update, it's not going to, then it will simply leave it as a simple long, nothing else. But if you end up losing the race for the compare and swap, so if compare and set comes back as false, what they then do is they create an array of cells. So that is this over here, array of cells. And each cell is going to be about 128 bytes. It's quite large. They make it larger than it needs to be in order to prevent false sharing. There's a very high chance that the cells would be living on the same cache line because it's created inside an array. So they make these cells bigger to avoid false sharing, and that means that, and also have an algorithm using the seed of your thread local random per thread seed in order to reduce the probability that multiple threads will end up in the same cell. Because if you have all threads going to the same cell, you're back at the atomic integer, atomic long. It won't help you to do that. So your cell, the way that the threads are assigned to the cells will reduce the probability that multiple threads go to the same cell. And so what will happen now is that if you lose the race again, it will again double the number of cells. It'll keep on doubling it up to a certain level. So for example, I've got 12 cores in this machine. Because runtime.getRuntime is available processors is 12, it will never have more than 16 cells within my array here. And this is important because each cell is quite large. It's 128 bytes versus, or even a bit bigger than that, but it's at least 128 bytes. They make it big on purpose, as I said, to prevent false sharing. And this way, you can actually end up not having too much memory being used on these long adders. All right. So, of course, if we can avoid all contention, that's even better. You know, the more you can avoid that is better. So the best way to deal with contention is not to have any. All right, another one is the starting gun synchronizer. Now, let's say I've got a service that I want to start. It takes some time to start, and I want the other threads to use the service, or the other parts of the system to use the service, but it must be available, and we don't want them to, we want them to wait until it's been fully initialized. But I don't want interrupted exceptions everywhere. So I could use something like the countdown latch, and it's pretty close to what I want, but not exactly, because I want it to be uninterruptible. So I've defined an interface called starting gun, and it's got a method wait uninterruptibly without interrupted exception. It's got the ready, and once the service has been set up, that will call ready, and all the threads which want it can now start. And so here's the first solution. Here what I'm doing is I make the wait uninterruptibly synchronized, I make the ready synchronized, I've got my ready Boolean equals false, that's how I start, and I clear the interrupt at the beginning, thread interrupted is set to false afterwards, and then I say, while not ready, I wait, and if I get interrupted, I will simply make a note of that and keep on waiting until I finally finish and I am ready, and then I'll say, if I was interrupted, I'm going to re-interrupt myself and continue. So the thread will exit in the interrupted status if it was interrupted, but it won't exit with an interrupted exception. And ready over here will say ready equals true, and notify all the threads that might be waiting for this state. So this sort of works, but there is a problem. And the problem is that if you're sitting on Java 21 and you want to use virtual threads, you're out of luck, because virtual threads are not fully compatible in Java 21 with wait, synchronized wait. It works fine in Java 24 onwards, but not before that. So another way to do this is to delegate to the countdown latch. And what I've done is I've stored the countdown latch inside as a private final. So this is a normal java.util.concurrent class. And if there's any bug there, hopefully they'll fix it, and we'll get the bug fixed as part of our package as well. And then we await uninterruptibly. Code's very similar to before with interrupted handling, but I'm delegating to latch to the wait. I don't have to synchronize myself. And this is fully compatible with all versions of virtual threads and Lua. All right. Both of those solutions would cause interrupted exceptions. We're hiding it, but we're still paying the cost of the exception being constructed. So another way to do this is to copy what countdown latch does. So what we could do is the following. We can go to countdown latch and see how it works. Now, the funny thing with the Java concurrent classes is that they actually are in the public domain. The other classes in Java are not in the public domain. These are actually in the public domain, except for one. Everything else is the public domain. And they've got the sync class, so we're going to copy and paste that over into ours, abstract Qt synchronizer. And the count is always going to be 1, so we don't need to have that. It's always going to be 1. And we don't need to have get count because we don't care what the count is. And then these two methods will keep as they are, straight copied and pasted from count on latch. We don't need to know how this works. And then await uninterruptibly, we need to have an instance of that. So we're going to have private final sync equals new sync. And then await uninterrupted, we say sync.try.acquire shared of 1. And we'll see this also if we go to the countdown latch. We'll see how that works. So that's the await method over here would say acquire shared interruptibly. But now we don't want to be interruptibly, so we simply leave out interruptibly. So we're going to say simply acquire shared, and then ready would be sync.release shared. And that's, again, the same as you'd see in the countdown latch. In the countdown, you'll see release shared as well. So it's copied and pasted from the countdown latch, and that means that if they discover a bug in the countdown latch, we are going to have to change our code because we've simply copied and pasted how they do it. Hopefully we won't. Hopefully that'll be fine. And just to make sure that it works, and just run the test because I'm doing a demo whilst you're watching, which is not so easy. So I've got some tests just to make sure that it actually was correct. See, I'm not very confident with this one, but I think I got it right. All right. So which one's the best one? I actually think that the second one is the best one, if you can afford the cost of the additional exception. It's compatible everywhere, and we've delegated the problem to the countdown latch. All right. Another thing which is quite interesting is the way that link blocking queue works. And I went into this in incredible detail, far more than I should have. And the way that this works is that they have two different locks. One is for putting and one is for taking. This means you can add elements to the queue at the same time as another thread is taking them out the front of the queue. At exactly the same time. And that causes a problem because there are two different locks, which means you can't be sure that if one thread is writing, the other one's reading, that they see the same information. You might have visibility problems. And so what they do is they actually have a shared volatile, which they store inside an atomic integer, and that's the count that they use, and they sort of piggyback off the count in order to ensure visibility between putting and taking. Very subtle. And if you look at that, you'll see lots of comments inside the code explaining how it works. If that wasn't a volatile shared value, it wouldn't work. They don't need that in link blocking deck because they have a single lock for reading and writing. But if you have multiple locks for reading and writing, you need to have some other way to ensure visibility. All right. Now, what's interesting is that if you have the single producer, single consumer, one thread writing, one thread pulling, you can actually have a better throughput than with this one than if you have a single lock to share. But we might end up with some surprises. So this is now another demo. This one is a bit more difficult, so I hope I'll get this one right. So I'm going to simply start by saying linked blocking queue. And I'm going to also give it just a 1. So what that's going to be, this is going to be a blocking queue over here of, just call it a queue. And it's going to be integer. And I'm going to have here, these are going to be the consumers, consumer count. So what I'm going to do is I'm going to create a blocking queue that's going to have a number of threads putting on there, and one thread putting on and a number of threads taking off. So we're going to have 10 million integers onto the blocking queue. So we're going to have, first of all, let's make a pool of a executors.new cache thread pool. Don't you love this AI always doing the wrong stuff? So we're going to have pool.submit. We're going to have we're going to have 0 up to 10 million. There's going to be the producers. There's one producer putting it on. So it's going to be q.put I, or let's make it 42, so it doesn't have to construct objects whilst you're doing that. And if this happens, you're going to print a cancellation exception. Interrupted. So that's a good option if you don't know what to do. So we're going to throw an exception if it gets interrupted. All right, and then we're going to do the same for the consumers, but we're going to have a consumer count here, and it's going to be called C, not I. And we're going to have up to 10 million divided by consumer count. So I'm just going to have 1 or 2. I won't have like 3 or something like that. So that it will be divisible. All right, so this is going to be now calling take and taking it out. All right, so, and this is now blocking queue. It's going to be a single producer, single consumer. And of course, we're going to do a try catch around that. So actually have a, yeah. Did I do this correctly? Sorry, no. So I'm just going to do this again. Time, it'll be the, let's call it time. Okay, let's run that once and just see what happens. As I said, this is a tricky exercise to get right. Okay, so we'll do this 10 times and see what it looks like 10 times. So this is with a single producer, single consumer, and sometimes when you run these tests, you get this bit of a spillover. You can see that all of a sudden it's 1.1 seconds, and that often happens because you end up with a lot of objects being constructed and the GC kicking in at exactly that time. So we can limit that by giving it more memory and see if that helps. So we can say minus x mx, let's put 31g, minus xms 31g minus xx, plus always pre-touch, and see if that helps a bit to reduce and to get more consistent results. Now, it doesn't seem to help too much, but we probably have to also, so it's all over the place. Let's also add a system GC or afterwards. Now, this is generally a bad idea to do this, and in fact, there was a very strange bug with link blocking queue to do with system GC. But for our example, hopefully once we do this, it'll settle down. So you're looking at about 650. Occasionally, you've got some big GCs happening, so that interferes with it. All right. So we're looking at 650 being sort of the best. Let's do it with 2 and see how that works. So 2 consumer, 1 producer. So before the best was 650. Now the best is sort of 930. It seems more stable. Not quite sure why. Probably because I'm doing the demo. And now if I change this to be an array blocking queue, and I remember the best we had, let's make this 10,000. The best we had before was 650 milliseconds for the link blocking queue. Now I've got the array blocking queue, and we'll see if we can beat that. So the array blocking queue is not as fast as the link blocking queue for single producer, single consumer. All right. Let's try the array blocking deck. Sorry, the linked blocking deck. I won't give it a size. I'll give it an unsized version. Also with 1. And we'll see how fast that is. Okay, so it's again similar. I'm looking for the best values here because I know there's a bunch of stuff interfering with the GC. So look at about a second. So the link blocking queue was the fastest with like 650, and this is about a second. All right. Good. So let's try it with 2. So now we're going to change this to be, oh, hold on. No wonder I got confused. Let's do this again. I was actually doing linked array blocking queue and link blocking deck. I just want to say link blocking deck. So this is link blocking deck. I should have printed out the type of class. This is the link blocking deck. The other one was mixed up with array blocking queue, so it wasn't really what I wanted to have. So link blocking deck, you're looking at about 1.2 seconds. The array blocking queue was about a second. And you've got a lot of contention because when you're putting and taking, this is clashing with one another. Okay? Whereas the link blocking queue with 1 was a little bit unstable, but I think that's the GC. But our best results were actually quite good. Right? So 560, 700. Okay, sometimes it's bad, but that's the GC throwing things around. All right. Now, let's try with 2 threads with the array blocking queue. So 2 consumers and 1 producer. Look at that. It's like way faster. And the link blocking deck with 2, it's also way faster. Now, where does this appear? Well, what's interesting about this is the link blocking queue is used by the fixed thread pool. Right? So, if, for example, you write a demo, a test, you want to see what is faster, having 1 thread in the fixed thread pool or having 2 threads in the fixed thread pool. Well, if you've got 1 thread in the fixed thread pool, there's no contention on the take. You can put jobs into this fixed thread pool as fast as you want, and you've got 1 thread who's simply taking them out from the front of the queue. No contention. Because it's two separate locks, or very minimal contention just on the volatile. But if I've got 2 threads inside the fixed thread pool, all of a sudden I've got the 2 threads, consumers, fighting for the front of the queue, and my producer putting jobs in, and you'll actually find that a thread pool with 2 threads is slower than a thread pool with 1 thread, because they're fighting for this link blocking queue. For that particular case, it might actually be faster to take something like a link blocking deck, for example, or an array blocking queue, or in order to reduce the contention of that. All right. Another topic which is quite interesting is inside the array blocking queue. Now, the way that the array blocking queue works, it's basically a circular array structure. So it's a fixed length, you say, for example, 10,000 or 100 or whatever you want, and you put elements on, and then what will happen is that once you reach the end, you're going to start writing at the front again. Of course, until it's full, then it blocks you. And here's my array blocking queue of size 10. I'll put in 5 elements, 1 through 5. And then if I have a bunch of different, I make an iterator, start iterating over it. If I then add more elements, I'm still going to see what has been added most of the time. And this is called weakly consistent. You don't get a concurrent modification exception, but you're going to try and see all the elements that are there. However, with the array blocking queue, you've got a limited capacity where elements can be. And if you write around the queue, you can overwrite what was there before. And so once you overwrite, somehow the array blocking queue has to notify all its iterators that it no longer, that they can't do weak iteration on there anymore. And so what they do is they do something quite interesting. This is not going to be a coding demo. This is going to be to show you the code. Not this one, this one here. It's basically inside the array blocking queue, they've got your iterator, which is an iterator. And the first time that you construct it, it adds it to basically a list of weak references, which are then used by the iterators class. So there's iterators class, which contains the nodes pointing to all the iterators with weak references. And that means that it won't prevent the threads, the iterators from being garbage collectors. So this prevents a memory leak. So it's the only class I know in the JDK where they keep track of all the iterators. The last one is the copy and write array list. And this is quite interesting because they, inside the remove method, they try to really avoid locking until it's necessary to lock. So if you remove something, they're first going to check, is it actually there? And the reason is this is an order n method. So if they were to lock the entire time whilst they're searching if the element's there, it would cost quite a lot. So there's some really weird code here. I want to show that to you. If you look at remove, first of all, they get the current array. It's a copy on an array list which will change as you go along. They then find out whether the object is there. If it is there, then they call remove again, which means they have to look for it a second time, see if it's actually there. So what they do is a second time around, they check, has the snapshot changed since we searched? If it has changed, we need to look again. If it hasn't changed, we can simply delete it, otherwise we have to check again. Now, this is quite interesting code, and you often find code like this in the java.util.concurrent library. We've got a label inside an if statement. Right? And you go like, why would they do this? Like, why would they write code like this? Why would they do stuff like this? Why can't they just, write normal code? This is ridiculous, having a find index label in there. And basically what they do is if they find it, they can jump out with break find index. I think if they, something like that, if they find it. So, and the reason is that they try, when they craft these methods, they try to write them in such a way that that the code is easy to optimize for the hotspot profiler. And so the code sometimes doesn't make much sense. Sometimes it looks overly optimized, and it is overly optimized. But that's what's going on here. They basically say if the snapshot not that snapshot, they go up to that index, search for it, and if they can find, they'll break out if they need to. But this means that they can reduce the amount of duplicate code. So what I tried, when I looked at this in a lot of detail a couple of years ago, I tried to rewrite it without the labeled break, and it was possible, but in the end there was a bit of duplicate code, and it could actually make the method a bit larger and therefore not as optimizable. All right. No, that's the wrong one. Hold on. There was this comment is wrong. I don't know why I put this comment in here. All right. So conclusion. Yeah, make sure you sign up to my newsletter. But conclusion is to basically use those classes which a lot of other people use. That's really what you should be using. Don't use classes that nobody else uses. Make sure that you use classes that are used very, very widely. So we've got a couple of minutes, 5 minutes for questions before they turn off the lights and put the chairs up on the tables here. So let's have any questions. Yes, sir. Now our microphone has disappeared.
I can come closer.
All right.
Give me a second. I would expect to see these benchmarks performed in JMH, not in the...
Yeah, I can't do that on the stage.
Kinda.
Nah.
Not as fast.
No. JMH needs hours to do it properly.
Yeah, you can write it and then demonstrate how to write it properly.
Yeah.
Thank you.
So yes, so that's a really good point. So the question is about JMH use, and you absolutely, when you do investigation, you want to do it with JMH. That's absolutely right. That's what I'm not doing a benchmark. I'm just doing a demo. Any other questions?
I have actually another question.
Yes, sir.
You told that concurrency bugs are hard to find to detect.
Usually, yes. Yeah.
I would expect to hear about JC stress.
Yeah.
Which makes it simpler.
Yes. Yeah, that's actually a good question about JC stress. And I actually wonder about that, because JC stress, a few of the bugs I found ended up in JC stress. Alexi added them in there. And just to explain what it does, JC Stress basically is a framework that helps. It's like JMH, but for concurrency bugs. And what it does, it simply gives you the framework to be able to test repeatedly a particular piece of code to make sure that it's thread safe or not. It's absolutely very valuable if you know where the bug is. To prove that there's a bug, JC Stress is great. But to discover them, it's very helpful, but it's a tool more to prove that the problem is there and to demonstrate it than to discover the bugs. And there are other tools. I mean, people have tried for many years, many generations, to produce tools that will automatically take your class and discover all the bugs inside, all the concurrency bugs. And it's very, very hard to do that correctly because you end up with lots of false positives, things that actually work, but they say they might be wrong. And I won't mention them all, but there are quite a few that have tried that. So yeah, definitely to check out. I'll add JC Stress for the next talk. I'll add it in there.
Thank you.
Any other questions? Yes.
Is there a source to know which classes I can use when I'm dealing with the trick? Like a document that shows me this was used a lot, this one.
All right, so the question is, which classes should you use when you're working with concurrency? As I said, use the ones which are used the most. And that was basically, you want to use concurrent hash map. Basically, try and use the ones which are the first two lines. Concurrent hash map, copy and write arrow list, concurrent linked queue, concurrent linked deck, future task, link blocking queue. And if you use anything else, you can. They work. And, I say I found 5 bugs in link blocking deck, but they're quite obscure bugs. Like one of the bugs, for example, I found there's a way that you can make a link blocking deck that has more than integer max value items inside, and the size goes negative. Now that's not going to happen to you most of the time. Right? I had to work really hard to create those bugs. Other times there's like maybe a race condition or something. But you want to use a class which are very widely used. And that's, again, talks against writing your own, because when you're writing your own, you don't have the number of users of these classes to find those bugs. Any other questions? Oh, it's like we're over time. So thank you very much and enjoy the rest of the conference.